the same type of galaxy. Okay, so the last 2 slides I want to show is kind of giving an overview of what we're now seeing and finding in this new channel. So what you see here is one of my models for double white dwarfs. So what kind of masses will we expect? And these are the ones that are merging. So here's the mass of one of the white dwarfs, and there's the mass of the hybrid. And I'm going to go back and forward between these 2 slides a couple of times. So bear with me. So anything in this regime, these low mass mergers, does not give rise to the type 1a. These are probably giving rise to our corona borealis stars. These ones, the mergers that happen between roughly equal mass white dwarfs, very massive white dwarfs, those are the ones studied by Rutger Pakmore, for example, and they find that those give rise to the very luminous type 1a that we're not finding in our models. If you go to a little bit lower masses, then again, based on their work, the other side, then they're finding these dimmer white dwarfs, 91 BGs. Now, in this part, so what we're adding is this part parameter space. That rectangular, those are the new sources that we're finding can also give rise to type 1a's. So if they're relatively massive, then their luminosities are bright enough to give a type 1a. If they're a little bit less massive, then they're not super bright. So the ones in this regime here are the systems over here that give rise to these subtypes. The systems over here, those are very dim. Again, those are the systems that are down here. They could resemble 2008 HA type supernova. And the stars over here, those are the ones that are giving those calcium-rich transients. So what is different in this regime compared to the others? Well, in this regime, it's the hybrid that's more massive than the other white dwarf. So that means that it's the other white dwarf that's being disrupted and accreted onto the hybrid star. So there's a thick layer of pure, relatively pure helium that ignites, and that gives rise to the gas channel. Oh yeah, lastly, because we're adding this large part of parameter space, what are the rates that we would expect? This is the rates, so just focusing on the blue line, these are the rates from OR. And in red overlay is the rates that we're finding on our modeling, and this is for the first time a channel that gives rates that is in the right order of magnitude of the type 1a rate. Here we're underproducing the number of type 1a's, we're still looking into that, but I think it's very promising that at least we're in the right ballpark of the type 1a rate. And that actually is bringing me to the end of my talk. So let me just summarize what I've been trying to say and trying to bring all of these topics together again. And that's, I think the future is very bright and very exciting, because with this wealth of observational data coming, there's so many more binaries and triples and stellar systems that I can play with and want to understand what kind of transients they give rise to. We now have code that we can use to study the simulation, the evolution of triples in a consistent way, taking thermodynamics, stellar evolution, and dissipative processes into account. Magnetic braking we will add. We're already finding that these triples do evolve differently from binaries. They experience mass transfer more often. The orbits are eccentric when the mass transfer starts. And there's many more fun channels to look into. For the transients, we're finding that these collisions are very frequent. Stellar collisions and triples would be the dominant way of getting collisions in the field. We're finding very interesting results for LIGO that might, that a good fraction of the LIGO sources could come from these triples. I think for double white dwarf collisions, that there are not enough of those white dwarf collisions in triples. I think there are not enough of those to get to the type 1a rate. But therefore we have another channel that explains the supernova type 1a congenital problem. And this channel involves a hybrid white dwarf that merges with another white dwarf. And we can match the spectra, the light curves, the range of energetics, the rates, and also the detonation. So there's a lot of these characteristics of the type-1As, a lot of the known problems that we're fixing in one and the same go. So I'll keep it to that.
So given the variety of, in this channel, the variety of initial conditions that you can start from, why is it a good standard candle or standardized candle?
That's a good question. So we do have this difference whether or not we find a detonation or not. The dimmest ones, of course, they don't do a full detonation. But there is type. I mean, in a sense, you're asking if type-1As are diverse, can we still use them as a good candle, right?
Well, we do use them, and in fact, they are claimed to be the level of 1% now with the Hubble constant discrepancy.
Yeah.
And so, but even just getting to that, it's surprising, given the variety of initial conditions that you can imagine in this channel.
Yeah, exactly. But there is a range of luminosities, right, that we need to explain, which is a problem.
The width is not too big. You check, it gives you a tight relation.
Well, you can. So our grid is not evenly distributed, right? So these are just the models that we used so far. So I agree with you. We have to check. Convolve it with my population synthesis to see how many of those would you expect, because these would be too dim with the Phillips relation, right? Yeah, so we have to see. But at least right now we're getting something that fits with the right range of luminosities, which is a first. So we have to start somewhere again. I think you were earlier.
Yes, I was. That's all right. Given that binaries, roughly 50% of the stars are binaries, it would seem to me that a non-negligible fraction of so-called triples could be double binaries. That is, instead of having a distant single star from a close binary, you have two binaries in relatively wide orbit.
Yeah.
And that would seem to allow lots of other possibilities. And I was wondering if anyone has looked into this, since it seems naively at least not to be a negligible population.
Yeah, so people are looking into four-body dynamics and how that would change the dynamical evolution of the system. As far as I know, it has not been, I don't think there has been any combination of stellar evolution with four-body dynamics, as far as I know. But in our code, we have the possibility of extending it in the future to actually do four-body dynamics. At the moment, I'm not doing that just yet because there's so many channels I still need to look into. But that's definitely something that we can start doing in the
Just seems to
future.
be not a negligible
Yeah.
population.
Yeah. So if I remember correctly, the triple fraction in solar type stars is 10 to 15%, and maybe I shouldn't say, right, because it goes online. But I think the quadruple fraction is a few like several percent. Does anyone know that?
Well, for the massive stars, actually, what we find is that this is a max, that the typical binary fraction, which is defined in a strange way, it's the number of companions a star given the mass, if it's the most massive in the system, would have. For stars above 10 solar masses, that binary fraction can be larger than 2, which supports development. But of course, the channels that Silvia is considering are the ones that are the most common. So obviously, it will be the work of the future and some really fascinating work in the future to go in this direction. But I think, as you said at the beginning, you have to start somewhere.
I think it's an interesting point that you're raising. So the triple fraction goes up as we're going to more massive stars. But I would guess that also the quadruple, like based on the few data points we have right now, that is also the case for the quadruple fraction. You had a question?
Yeah, I think your model is fascinating. So you're starting out, you have one carbon oxygen white dwarf and another that has this large layer of helium.
Yeah.
So there are models where people start out with a carbon oxygen white dwarf and a helium white dwarf. So what I'm wondering is if
So it's a good point that you're bringing, something that I forgot to say. So the moment that the lowest mass star is being disrupted and it forms this accretion disk, other simulations are showing that the material is completely mixed. So what we're accreting is carbon and oxygen that's heavily enriched by helium. Well, in the case of a helium white dwarf, it's fully helium, right? So it's different burning processes that happen. So it might sound similar, right? Because you might think that you're accreting first the outer layers of the hybrid. So wouldn't that also be completely pretty much completely helium? But it's a different material that you're accreting. And if you're accreting too much helium, you would see it in the spectrum. So that's the difference.
Can I follow up on Chris's question and ask you about in your M1, M2 merger diagram from your population calculations? Is there structure in the delay time, which would essentially say something about the host environments of the different subclasses?
See this one. So overall, well, this one, right? So in red, you see the normal type 1As. So those are the ones that we categorize in this regime. And then the blue ones are where we're adding these extra sources. So these are